We'll do some intros quick. I'm Sammy, CEO and co-founder of Eventual, um, where we're essentially building Daft, an open source query engine built from the ground up in Rust. My background has been in high performance computing and AI, and I've worked in self-driving for the last decade or so. I was CTO at a startup where we were essentially building autopilot for everyone else, and ironically enough, were acquired by Tesla. I stayed in self-driving, worked at Lyft level 5, where I met Jay, and I was in charge of a lot of the technical direction of perception. Over there, we built a lot of data systems and AI systems to make self-driving possible. So a lot of the time spent there was building systems that can handle multimodal data, things like images, LiDAR, radar scans, as well as the tabular data.
Yeah, so hi, I'm Jay. I'm the other co-founder at Eventual. In my background, I worked in autonomous driving where I met Sammy. Before that, I actually also worked in biotech at a company called Freenome, doing cancer detection with ML and AI. I joined these two really cool fields to do ML and AI, but at the end of the day, I found myself just working on data. That's kind of like at the heart of it all, right? Like you have data of different modalities, whether that's images or genomic data. And so I ended up building a lot of distributed data systems for machine learning. And that kind of led me to this world and led me to the world of Iceberg and this Daft as well, which is a data frame query engine. Yep.
Cool. So one of the things that I want to just take it over here. One of the things I want to quickly talk about is what does today's Iceberg stack look like? A lot of you are going to be familiar with this, but for those who aren't, let's just do a quick overview. So what does today's stack look like? As you can see here, it's actually composed of many different layers. At the top, we have data engines, also known as query engines, and these include things like Spark and Trino. What these query engines do is take a query from a user, analyze it, resolve the different things you're querying inside your query, and resolve them to be like, okay, this is a table that lives here, this is a table that lives there, and where it gets these references is a data catalog. So this engine will get your query, analyze it, figure out where everything lives, and then execute it over a cluster, giving you some result. Right underneath that, you have a data catalog. And these things include stuff like Amazon AWS Glue, Apache Hive, and Trino, which itself also has a data catalog. And you can kind of think of these as tables of tables. They're essentially a way to see, okay, I want to query this table, this is where it lives, this is the type of table it is, and this is how I actually access the data there. These tables are usually made up of some kind of table format. And these include things like Iceberg, which is the reason why you're here, Delta Lake, and Huddy. And these table formats are usually metadata layers that include information about what files belong to it, things like statistics, partitioning information, and different schemas that the table might have and have changed over time. The data of these table formats ultimately are in the Parquet format, or sometimes ORC. And these Parquet files are essentially columnar storage formats that can store all your data in a way that's really good for analytics. And these Parquet files would live in some kind of object store, like HDFS or S3. Now, this looks pretty complicated, and it typically is. But one of the things that made it easier historically was that all of these libraries are built on top of the JVM. And so when you are building a component or a new library or a new module for this, you can kind of link to the existing libraries and kind of just ship a JVM jar to then plug in with it. And so when you're shipping something like Iceberg or trying to use Delta Lake or something like that, you can kind of just plug in a module and operate with it. And this is something that we see quite common if you're running your own Spark cluster or using something like EMR. You can kind of just give it a set of jars that you want to use for it. Now, what does this also mean? This also means that if you're trying to use a language outside of this, it's quite hard. And so if we have, let's say, Jay, the Python developer, trying to use Python in the stack, it's actually quite interesting. So the most common way would be using something like PySpark, which is kind of like which is Spark, but with a thin layer on top that provides a Python API. So Jay now would, even though he just wants to do Python and maybe run some PyTorch model, has to kind of learn about the stack. He has to learn, how to set his Java home. He has to learn what jars are and figure out how to install the JDK. A fun thing that I've been asked, and actually is a common question asked in Stack Overflow, is how do you install Java with pip? It sounds ridiculous, but this is actually a common way of doing it. You install JDK, and you can install the JDK using Python. And so for someone in the Python ecosystem, this is very daunting and hard to maintain. Okay, so why should we care about Python? Ronald Shin, one of the co-founders of Databricks and one of the creators of Spark, has said that probably around 80% of Spark users use Python. And so that's a huge number. So 80% of people who just want to do Python have to learn about this whole JVM stack. And as we're seeing now more than ever, Python's kind of the language that we use for machine learning. And so if you're running batch inference, doing some kind of simple model like with something with sklearn, or doing large-scale LLMs, almost everyone is using Python. So it really can't be ignored here. So why is PySpark not enough? So let's actually talk about a little bit about how Spark would work, and then kind of go into how do we extend it for PySpark. So if you look at the right side of this diagram, we see essentially Spark workers. And the way that Spark would work in a way to execute your query is that we would have a cluster. We would essentially spin up Spark on every node in this cluster. And what we would do then is when you have a query, we would kind of figure out what parts of it to run on what parts of the cluster, send that work off, and then the Spark workers essentially get a part of a plan they want to run, execute a bit of it, send data back and forth to another, and give you the result. This usually works quite clean. You have this kind of monolith that contains all of the things you need to execute your query. And debugging this is actually not too difficult. However, if you want to run Python, what you have to do is run a sidecar that runs only a Python worker. And the reason for this is that the JVM can't really run Python. And so what we end up doing then is for every Spark worker we start up, we spin up like a sibling to it, which is a Python worker. And then when you want to run something in Python, we first use the Python API. We say we run in Python. We have to kind of like package it up and then send it over a connection to a next process, which uses Spark context or worker. Then that sends that over to other Spark workers, which then go over another pipe and then talk to a Python worker. And this pipe that talks between Java and Python is typically called a Py4J bridge. Now, what's the problem with this? Is that you kind of have to handle a lot of different cases. Let's say I am running a Python UDF and I have let's say I forgot a comma, when I'm writing a dictionary. So we essentially write a function. It gets serialized to the Spark head node or Spark context. That gets sent over to Spark worker, then gets passed over to a Python worker. Then when the code actually runs, we have an error. Then we have to get that stack trace, send it back to Spark worker, back to the head node, and then back to me. And so by the time that it goes all the way there and all the way back, we actually have like a 2,000 line stack trace, and it's extremely hard to debug. So the user experience here is just not great. The other expensive thing is when you're dealing with objects in Python. So imagine I want to use a data frame with a type that I have. Let's say I have an image type that I want to build. Then what that means is every time we go across this pipe between Java and Python, what I have to do is essentially package it in a way that Spark can understand. And this is usually quite expensive. There have been some efforts lately to use something like Arrow to do shared memory between Python and Spark, but it's limited to the types that Arrow supports. Cool. I guess the other thing is that if you're trying to use any kind of hardware acceleration, this is also very difficult. One common workload we did in self-driving is we use something like Spark to actually run inference over a lot of images. So imagine you have like a bucket full of images, and I want to say, hey, does any of these images have a dog? And what you would do is write that query in Spark and use something like a UDF that uses a GPU. And this whole process was very painful because what we'd essentially have to do is kind of configure Spark and Kubernetes to make sure we don't schedule more than one, let's say, Python process per GPU, or we don't schedule more than one GPU to one Spark worker. And this takes a lot of configuration. And if you're trying to use something like EMR, this is also very, very difficult. Cool. So what is the ideal Python solution? So first is that we don't want to use the JVM and don't do a Py4J dependency. This means that everything we want to run should be in the same process, whether it's Python or some other native language. We want things to be fast locally. If we have a large node, we want to be able to scale it vertically, and we want it to be native and vectorized. What that means is that we want it to either be written in C++ or Rust, and when we write code that, let's say, does a large aggregation, it should leverage the hardware acceleration that CPU might have. We also want to do distributed computing. So when we encounter data sets or workloads that are larger than what one node can do, we want to be able to use more than one node. And so this is called scaling horizontally. And this is quite common for read-intensive workloads. We want to be fast in the cloud. What this means is that we want to design our engine to work well in the type of machines we encounter in the cloud, utilizing things like ARM CPUs or the kind of clock rates we see on like EC2 machines. But we also want to design our engine to operate well around object storage. This means that we should be really fast reading from things like S3 and GCS, and also be able to write to it quite efficiently. We want to leverage efficient query planning. So when we get information from catalogs like Iceberg, we want to be able to like use the information there and do things like partition pruning, more intelligent joins, and better sorts. And finally, we want to have a rich set of ecosystem integrations for Python. So our tool should work great with NumPy, PyTorch, Pandas, and like Ray. Cool. So let's go into the 2024 ecosystem for Iceberg. Well, we kind of imagine, let's do a quick comparison of what it looks like for Java and Python. So in Java, we have JVM libraries like we talked about. We have Iceberg, HDFS, Parquet, and they're all usually Java libraries. So extending that to another language is usually quite difficult. There have been some efforts with using something like JNI to then talk to native libraries, but that work is usually quite difficult to do. When we want to scale out, the typical way that we would do that is run it on Spark. And so we would have these libraries, and then you kind of use Spark as kind of the execution engine and a way to use as a distributed runtime. Now, if you want to do native machine learning using the library, the main way you would do it is using Spark's MLlib. When you're trying to use something like PyTorch or a native Python library, you would then have to go through a Python UDF. Now, what does this look like for Python? So with Python, it's actually a lot more composable. Instead of having these big monoliths, we actually have these small composable units that we can put together. And so in terms of languages, because we have these small composable units, we can actually use these interop C++ and Rust libraries. So things like PyArrow, PyIceberg, and Daft are actually written in native languages like C++ or Rust. And this kind of lets us use the kind of have the best of both worlds, where we can have very efficient libraries but still use them in Python. This is kind of the same paradigm that PyTorch and NumPy do as well. Now, if we want to horizontally scale, we don't only have one choice, we have multiple now. The most common ones would be something like we can dispatch our work that we want to do on things like Ray or Dask, which are both distributed runtimes. Now, for MLAI, we're kind of, our choices are kind of unlimited of what we can use. Instead of just being forced to use MLlib, we can use kind of the whole PyData ecosystem, things like Pandas, things like SciPy, PyTorch, and many others. So what does this look like for the single node case? Let's say I'm just working on my laptop and I want to be able to read Iceberg. What this look like is something very similar to what we saw before, but the key difference is that the data engine side is actually made up of multiple units now. So instead of using Spark directly, we can use something like Iceberg, which is the official implementation of Iceberg for Python. I think there should be a talk in this session as well by Paco. So the way that Iceberg would work is you can actually use Iceberg to query your Iceberg table, and it can read data from S3, read the metadata, and then actually emit out a series of arrow tables. And so you could give Iceberg the predicate you want to run on the table you want to run, and it would just give you the tables that then can be ingested from Pandas, Polars, and Daft. And the thing to note here is that all metadata and data operations are flowing through Iceberg. Now, we have a way now to read Iceberg data in a way that uses no JVM. However, the limitation of this is that we're kind of limited to just running on a laptop or a single node. Now, if we want to go to distributed, how could we do this? And the answer is we can still use Iceberg. However, the key difference is that we're now using Iceberg only for metadata operations. And so in this case, if you're running a Daft query, you can actually ask Daft to read an Iceberg table, give it, let's say, some predicates you want to run, and maybe some global operations you want to run, like a big sort. Then what Daft will do is give these constraints to Iceberg, which will then hit like a catalog like glue, read the table format, and then forward the metadata files over to Daft. Daft will then get these metadata files and then actually distribute it over the cluster and then read the actual data, which is Parquet on S3 usually, in a distributed fashion and execute the query quite in a horizontally scaled way. So this kind of enables distributed reads, distributed queries in Python with Iceberg. And as far as we know, it's like the only way to do distributed reads in Python currently with Iceberg. Cool. Now it's time for a demo, and I'll hand it off to Jay.
All right. I guess I'm the demo man, not demolition man, but I'll run the demo. Okay. So yeah, today we'll be going through a demo on how the integrations of Iceberg and Python look like. And so we'll be talking through a lot of the query engines and libraries that we mentioned before, including PyIceberg, Daft, Polars, Pandas, etc. And then we'll also actually be running some distributed computing, right? That's all kind of very, very exciting and easily accessible now through a library such as Daft. So first of all, I'm going to be able to run a couple of installations. So pip is the package manager for Python, and it's extremely easy to use. You just run pip install. And so right here, I installed PyIceberg, which is the officially supported Iceberg implementation of Python. And then on the second line here, I'm installing all of our query engines. So we have Daft installed with Ray support, which allows us to run in a distributed manner. Then we install also Polars and Pandas. And then the rest of the installations here will allow our tutorial to run. But these are all just very, very simple Python dependencies that you can install. And a lot of them are actually already natively built for your machines. So you'll be downloading what Python calls wheels onto your machine, which are pre-compiled versions of these libraries that will run immediately, extremely easy to set up. So let's go through this tutorial step by step. First things first, we'll go through some of the PyIceberg basics, right? Using PyIceberg, it's now very easy to manage your catalogs and namespaces and tables. You don't have to use SQL anymore, which is extremely, in Python, it's very easy to use because it has that kind of like feel as a programmer and makes it very easy to work with these objects. So let's run through a simple example of how we can create a table and then write and read back from it. The first thing we will do is we'll go ahead and create a catalog. This is, I believe, unique to the Python implementation of Iceberg, where you can create a SQL catalog on a location on disk on my machine currently. So what this looks like, after I've ran this, it's going to create a file inside of this location, /temp/warehouse. So let's see what that looks like. If I run tree here, you should see that it starts creating the catalog. And 1 second, warehouse tree. Yeah, so if we look at our /temp/warehouse location right now, you'll see that a catalog has been created. Right? We have this PyIceberg catalog.db object. This is just a SQLite file, which now serves as my local database, and this makes it extremely easy to just get up and running with Iceberg on your local machine. We can now create a namespace under that catalog. Namespaces are really just collections of tables under the catalog. So after running this create namespace object, we can create a table. So you won't see any new things happening in your folder until you create this table. But let's go ahead and create an extremely simple table. It just has 2 columns, a name and an age. The name of my table is my friends, and name is a string type and an integer type. So everything here you're looking at is easily doable from the PyIceberg library, which allows you to create schemas just like so. The nice thing also about running in Python is that it gives you all these really nice auto-completions, right? So if I do like catalog dot and I press tab, it shows me everything that I can do with the catalog object. And so if you want to use a catalog, you want to create a table, you want to drop a table, you might want to list all the available namespaces and tables. That makes it extremely easy to do all through Python. So let's go ahead and run this. This should now create our table object. Let's see if it created anything different in our tree, and we see that it has. So now that our table is created, you'll notice that more data has been added to our Iceberg folders. So you'll see that under the namespace, which is called my namespace, I now have a table called my friends, and it has a bunch of metadata. No data yet because no data has been written to the table. This is the very first metadata commit on our Iceberg table. So let's go ahead and print the Iceberg table. It's going to show you that it has named my friends, and here's a schema that we defined earlier, and it has no partitioning, right? Now that we've looked at the metadata for the table, let's go ahead and write some data to the table now. We can very easily do this with a library such as Daft, where here we are creating a Daft data frame, right? Very simply, a data frame with 3 rows, just Jay, Sammy, and Brian, and then here are the ages of Jay, Sammy, and Brian. And we're going to go ahead and write this data frame to the table that we just had, which is extremely simple. Data frame dot write iceberg, pass in the table object that we had from before, and we specify that we want to overwrite all of the data in this table. So after running this, Daft actually gives you a really nice visualization of what actually happened under the hood. It's going to tell you that, hey, your operation added 1 file. This file has 3 rows. Here's the file size, and here's the file name. And what's really cool if you're running this on a local demo is that you can actually see that file. You'll see that a file has been written in the data folder now with this Parquet file matching the Parquet file that Daft told us was written. And you'll also see a whole bunch of other metadata that has made it into your folder, right? So under the hood, what happened was that Daft wrote the Parquet file, then used PyIceberg to commit the new data to your table. All right, now that we have a very simple table, let's go through all of our options for reading the data. First of all, we have this ability to read data on a single node. A little bit of recap. How this works is that these query engines, such as pandas and polars, will be able to use PyIceberg, which handles all the data and metadata operations, and then converts the resulting data into the arrow memory format, and then passes that over into our query engines. So what that looks like, extremely simple. Here's pandas. It runs an eager materialization, right? So the moment you call .scan.toPandas, this will run a read through PyIceberg, convert it into arrow, and then present you with a pandas data frame. Here's polars, which is slightly different from the pandas implementation in that it's what we call lazy. And so you can call polars.scanIceberg. You pass in the table object, and this creates a lazy polars data frame. But what it will do is that once you execute this data frame, it's going to be able to push down any filters into PyIceberg so that PyIceberg can then read your data and metadata efficiently. But it's still going to read everything through PyIceberg, convert it into the arrow format, and then pass it over to polars, right? Which means that your workflow is kind of constrained in the single machine, single process environment, and can't really scale horizontally in the cloud. Here's a different way of doing it. So Daft does things a little bit differently, where it just uses PyIceberg for the metadata operations, and it does its own reads of the underlying data files. So with Daft, you'll notice that similar to polars, it's a lazy API. So Daft is also going to be able to push down any filters into PyIceberg so that PyIceberg can do all of its pruning and hidden partitioning really effectively. The other thing that Daft will do is that Daft has this plan where we can look at what it's actually doing. And so for this operation where we read the table, Daft is now telling us that there is one scan task, which is roughly equivalent in Daft to one file that it needs to read. It's going to tell us how many bytes it's going to read. But the important thing here is if we had, say, 1,000 scan tasks, Daft is actually going to be able to spread those scan tasks over the cluster and do those reads by itself without relying on PyIceberg. And so concretely, in this case, PyIceberg is going to be reading all of this metadata and then handing essentially file paths to Daft to read, and Daft is then going to be able to handle the reading of this data. And so let's see that in practice, right, by actually reading a much larger Iceberg table. So here's a larger Iceberg table that I have in my AWS Glue catalog. Let's take a look at what this table looks like. So this table has a schema. Here are all the fields in the table. It also, interestingly, has a partitioning scheme. It's partitioned by the month transform on the L ship date column. And so using Daft, if I want to read this table, I just call daft.read iceberg. And then if I call df.show, Daft is going to be able to very intelligently ask Iceberg, hey, just give me the first file so I can show the user some output. So here's what the table kind of looks like. The first 8 rows showing Daft is showing the first 8 rows of this table. Next, I'm going to run some very simple queries. So first, we're going to filter this table by the L ship date column. We want only rows where the L ship date is before the 1st of January 1996. Right? Notice how Pythonic all of this is. It's just using native Python to kind of construct this query. And the second thing we're going to do is we are going to group by the date, and then we are going to run an aggregation on the price. Right? So we just want to sum up the total price for every given date. So after we run this, we'll see that the resulting data frame that we get is just an aggregated data frame of 2 columns, the ship date, and then the summed price. And also, Daft will tell you, hey, if you run this thing, here's what's going to happen. Right? And here, there are a few interesting things to note. Number one is that Daft is, kind of has this fully fledged query optimization layer, where we're going to be able to do things such as predicate pushdown. And so this filter that we had from before, where you ran this L ship date filter, Daft will talk to PyIceberg, recognize that, hey, this L ship date is actually a partitioning column, and therefore, after we optimize it, we are going to get rid of this filter, right, and push this filter down into the scan as a partition filter. And Daft has all these inbuilt partitioning operations, such as the Iceberg months transform, that it's then going to be able to use when it reads from PyIceberg and utilize PyIceberg's really efficient pruning of data files by passing this filter directly to PyIceberg. So that's number one. Daft does these really cool query optimizations that can leverage PyIceberg. Number two, what we notice here is that Daft does a distributed read, and it's going to tell us up front, hey, warning, red lights flashing. There are 280 scan tasks here, right, which roughly corresponds to 280 files under the hood. It's also telling us that, hey, warning, you're going to be reading a lot of data. This is about 90 gigabytes of data. And so this is not something I want to do on my local machine, right? Right now, if I do it, our Wi-Fi bill is going to go crazy, and it's going to take a really long time. And so now, given this information about the plan, Daft is going to tell me that this is a fairly expensive query to run and involves a lot of I/O. And so a great solution here is to actually run on a cluster that sits in the cloud, because two things. Number one, this cluster is going to sit in the cloud in the same region as where our data is. So that means that we have much higher throughput of reads from cloud storage. And number two is that we're going to be able to spin up more machines. And these machines will have a higher aggregate network bandwidth, allowing our workload to run a lot faster. So let's go ahead and restart the notebook. And I'm now going to run Daft, but on a distributed cluster. So prior to this, I already spun up a cluster. It's a Ray cluster. And so here's the dashboard of that cluster. This is what Ray kind of looks like. Our cluster has, here we have four worker machines and a total number of CPUs of 16. Right? Under the hood, if you look at the Ray dashboard, it's going to show you here are the 4 worker machines. So, sorry, you weren't able to see my dashboard from before. But here, you'll see that there are 4 worker machines, and they are all currently kind of idle, just like sitting, waiting for work. So in order to run Daft on Ray, all you have to do is really simple. Just point Daft to Ray to say, hey, Daft, set your runner to the Ray runner, and here's the Ray address. And from here on out, everything that you run in Daft is going to be natively running on this cluster. And here, I'm going to show that in just a second, where right now we're going to run this very same aggregation that we saw from before. So this is reading the table from Glue, and then running the same aggregations with exactly the same syntax. But now we're going to be able to run our aggregation on Ray. And so as I run this is no longer running on my machine. Daft will kind of farm out the work onto our Ray cluster. And if we refresh this, we should see that our Ray cluster is now doing some work, where the CPUs are now occupied. Right? There's a whole bunch of work happening on the Ray cluster now. Each worker is doing a bunch of reads and a bunch of work. Also, interestingly, if you look at what work is actually being done, you'll see that most of the work, as we expect, is actually being done in the read stage. And so all these like gray and red boxes you see here are actually Daft running the scan task work, which takes roughly about 1.6 seconds per scan task or per file. And that takes up the majority of the workload. Everything else happens really, really quickly. And so by spreading all of these red boxes out amongst all these the 4 nodes, is worker 1, worker 2, worker 3, and worker 4, we can spread out the work amongst all of these workers and have this all happen in parallel, which gives us that really powerful distributed computing that we were looking for. And now the query is done. We'll see that the query finished in about 50 seconds, and here are the results from that query that we just ran, which would have been extremely expensive to do on my local machine because of just networking. So to recap, none of this code in this tutorial involved the JVM at all. We were able to run everything just through native Python and Python libraries that we just pip installed. So that's really, really cool. It's something that wasn't really possible actually just maybe a couple of months ago. Everything is incredibly easy to get started locally with simple pip installations, which is extremely familiar for any Python developer. And this stuff is fast, So if you're thinking in terms of performance, Daft is actually much faster, about 5x faster than Spark on many workloads. And then Daft is also as fast as something like Polars or DuckDB when you run locally. And the third thing that we saw is that we're able to scale into the cloud, And it's extremely simple to do. It's just a one-line call with a framework like Daft to run in the cloud and horizontally scale your workload in order to take advantage of all the memory and computational resources and network bandwidth that's available to you on a cloud machine. So that was it for the demo. Now let's talk a little bit forward-looking. Where is Iceberg and Python kind of going? So when I think about the Python ecosystem, there's really 2 main ecosystems. The first is the local data science story, where it's just someone in the notebook running everything on their laptop on a single machine. So PyIceberg is rapidly building and improving here. And any PyIceberg improvements directly improves that local data science workflow, because really PyIceberg's job in that case is just grab as much data as it can from Iceberg in the most efficient way possible, and then convert that into a pandas format, like a polars format, through Apache Arrow. And so this is going to be extremely exciting over the next year as PyIceberg becomes more and more powerful and can do this in a much more efficient way. The second thing you will want to do in the Python ecosystem is to run data engineering or ETL at scale, or things with a machine learning flavor here too. And so Daft is building together with the PyIceberg project to bring all the functionality of Iceberg onto the Python ecosystem. And soon you'll be able to run anything that you could previously in PySpark just through Daft. So this would include even things like if you need to do table maintenance operations, like orphan file pruning, or if you need to run like a large machine learning job, batch inference over all of your Iceberg data, or like even a training job over your Iceberg data. That's all going to be possible now through Daft. What this means is that Iceberg is going to be incredibly powerful for your organizations, because now using Python, it can handle all the different use cases across analytics, data engineering, and machine learning and AI, which is where Python is kind of very uniquely suitable for. So some things are on the roadmap for the Daft library. We are building a lot more of the Iceberg features. So merge and read, that's coming soon to Daft. Partitioned writes are also coming soon, pending the release of PyIceberg 0.7. And so we're working really closely with the PyIceberg team here to allow for writes to partitioned tables. We are also starting to build some functionality around partition scheme evolution. And so if you're changing your partitioning scheme as you move along, Daft will be able to handle that very soon. And lastly, we'd love to collaborate. And so if you bring any of your Iceberg features, things like puffin files, I know there was a great talk yesterday on that. We'd love to work together with you to make all those features available through Daft and to leverage all of these Iceberg features for extremely efficient reads in Python. So separately, away from the just pure Iceberg domain, we also have a lot of exciting things coming up on the Daft roadmap that will bring us a lot closer to the feature set that something like Spark provides. So one thing that we are doing is we are collaborating with Amazon to bring to you petabyte scale shuffles. So these are extremely large shuffles, So imagine a giant petabyte scale sort. And Daft is going to be able to give you that reassurance that no matter how big your workload, Daft is going to be able to handle it for you by scaling horizontally in the cloud. The next thing we are working on are our cost-based optimizations. And so adaptive query execution is coming, What that means is that Daft is going to be a lot more intelligent. As it's running your query, it's going to be able to analyze the data in your query and perform all these crazy optimizations on the fly, instead of you having to manually tune your query as you look at metrics and things like that. And one thing that we have heard from a lot of people is that it's really painful to tune all the partitions and understand how many partitions you need at various points in a workload. And so Daft is going to be able to do a lot of that for you as well by doing automatic partition rebalancing as we execute workloads. And the last thing, I know this is a Python talk, but Daft is also going to be able to bring you SQL support very soon, which is something that we've heard from a lot of people. Interestingly, a lot of people run actually SQL from the notebook. And so inside of a notebook, you might be running some SQL. And Daft is going to be able to bring that to you very, very soon as well, targeting dialects such as Trino SQL and Spark SQL so that you can have that parity that you're looking for when you're moving a workload over onto Daft, the Daft data engine. So yeah, that's kind of it. If you like what you see, come chat with us. We'd love to collaborate. We are also hiring, right? So if you are interested in things such as databases, data systems, come chat with us, cloud systems, cloud infrastructure. Here's my email at the bottom. Feel free to contact me. And also, Daft is fully open source, right? So you can find Daft and keep up with all the work that we're doing at www.getdaft.io. And if you're already in the Python ecosystem, that's great. Here's how you install it. Just do pip install get Daft, and you have everything you need to get started. That's it.
All right. Thank you, Sammy and Jay. I would like to now open it up for questions. I know we already have a few questions that have filtered in. So once again, please use the Q&A tab towards the top right. We've got roughly about 5 minutes or so. So I'm going to try to get through these quickly here. All right, first and foremost, what is the difference between Daft and Ray?
Do you want to take on? Or?
Sure, yeah. So Ray is a distributed computing framework. So you would use Ray to start a cluster, right? But Ray is a fairly general purpose distributed computing framework. And so the API that it provides you as a user, Ray Core provides you with an API that's just like submit work and receive results, right? But what Daft gives you on top of that is all these primitives that you expect for data processing. So things like joins, sorts, group by, aggregation, reading from Parquet, which you don't get from Ray out of the box. So the way that Daft works is that it translates all of these operations that you want to run, like a sort, for example, into the Ray primitives and calls that it would then use to run on top of Ray. So if you have an existing Ray cluster, that's great. All you need to do is just point Daft to the Ray cluster, and Daft will automatically utilize resources on the Ray cluster for you. So you can think of it as Ray sits on top of, say, like just the machines, and then Daft would run on top of Ray. So the levels of abstraction that kind of happens in that order.
Got it. Okay. I guess this is a follow-up question to that. What is the relationship between Daft and Delta Cat project?
I see. Yeah. So we actually collaborate with the folks at the Delta Cat project, and they actually right now you can think of it as there's two levels of integration we use with Delta Cat. So one thing that when you use Delta Cat, they actually leverage Daft right now to do all of the Parquet reads that they do. So Delta Cat will get a bunch of source files. We'll get a bunch of source files, kind of read them in, kind of shuffle them around a little bit, and write them back out. And they utilize Daft underneath the hood for that. The integration that we're working on with them right now is actually representing the data catalog that Delta Cat is backing with a Daft data frame. So you can actually just read Delta Cat and then use all the operations on Daft on the data frame and then push everything down into Delta Cat as needed.
Yeah, so I mean, just for some context too, Delta Cat is an open source project, kind of under the Ray umbrella, but it's maintained by the folks over at Amazon. And this is the project that Amazon uses. So every time you make an order in Amazon, right, all your data makes it into the Amazon's giant data lake. It's like petabytes, I think exabytes actually of data. And Delta Cat is a project that then does a lot of compaction and does all the data maintenance and deduplication. And so Daft is being used under the hood for all of these workloads. And interestingly, also, the Delta Cat project is looking to adopt Iceberg as kind of a table format. And so all of the work that we're doing together with the Delta Cat team actually translates very, very nicely to the Iceberg world.
Okay.
Ooh, I see a question about benchmarks. We should talk about that.
Yeah, so let's just get into that one, right? Is there a benchmark for Daft? It's a two-part question.
Yeah. So
Compared to Spark.
how do I?
Here's some hidden slides so we can pull those up.
Yeah, literally.
Slideshow on this.
Yeah, can you guys see this?
Yep.
Yeah. So for the top answer, so the one thing we did is these are new benchmarks we haven't put on the website yet. But when we run in a realistic workload that we try to emulate that we see with our users is that we spin up a cluster in the cloud.
Yeah, the EMR Spark.
EMR Spark versus Daft. We're using the same machines, and for reading data from S3 back in Parquet, we're about 7x faster than Spark. And so, as kind of Jay alluded to, like the beauty of Daft is that we can, be nearly an order of magnitude faster than Spark in the distributed setting, but then still be as fast as the native vectorized, like embedded databases like Polars and DuckDB on the local story. So we can kind of do both.
Okay. I think that's about all the time that we have for the question. So once again, thank you for joining us. And then also thank you once again, Sam and Jay, for a great session.